Okay, hopefully we'll have enough pin battery to get through this next example. So we're going to continue with examples that will have both an initial and a final value because they're essentially a step response. So let's look at this circuit. So the switch in this circuit is in position A for a very long time, which means we have a circuit where the switch is in position A. We'll evaluate that circuit at 0 minus. So in the instant before the switch closes, it's been sitting for a very long time. So we have the 5 kilo ohm and the 10 kilo ohm, the 75 volts. Here's our point A. Our capacitor's here, but because it's been sitting for a very long time, it appears to be an open circuit. So V0, which is our initial condition at 0 minus, is basically the voltage across the 10 kilo ohm resistor. So it'll be a voltage divider. So we have 75 volts times 10 over 10 plus 5, which I believe is going to give you 50 volts. So that is our V initial. So in our formula up here, that would be our X0, because for capacitors, X is voltage. The next thing we need to do is assess what is the time constant. So let's move the switch, because we always evaluate tau for t greater than 0. So when the switch moves and connects to B, the left-hand part of the circuit is out of the circuit. So what we have is we have a 40 nanofarad. We have 40 kilo ohms. We have 10 kilo ohms. And then we have this DC voltage source. So to evaluate tau, we want to kill the source, which means we replace it with a short. When we replace it with a short, the capacitor and the two resistors all appear in series. So in parallel. So we can combine the 40 and the 10. We can combine those in parallel. That leaves us with a 40 nanofarad capacitor and 40 in parallel with 10 gives 8 kilo ohms. So tau is RC, which is 40 times 10 to the minus 9th, 8 times 10 to the third, or 320 milliseconds. Okay, so that gives us then an evaluation of the time constant. So we now have initial voltage, we have tau. So initial voltage is found from the t equal to 0 minus circuit. Tau is found for the t greater than 0 circuit with sources killed. Final voltage is found from the t going to infinity circuit. So as t goes to infinity, we have our, let me just move down here to the next page. So as t goes to infinity, we have our 40 nanofarad capacitor, and it actually is going to look like an open. So we have an open circuit, and the final capacitor voltage is going to be the voltage across that open. We have 40 kilo ohms, we have 10 kilo ohms, and we have plus minus 100 volts. This voltage will divide between these two, and based on the way our original voltage is labeled and the way our source is pointed, that final voltage on the capacitor, we need to put a negative sign because of the polarity of the source. So it's minus 100 times 40 over 40 plus 10 using voltage divider, or 40 volts. That looks off. 40 over 50, so 80 volts, and it's negative. Alright, so now we can plug into the formula. V of t is our final voltage plus our final voltage minus our initial voltage, which was, where'd we go? Where was our initial voltage? 50. E to the minus t over tau, which is 320 times 10 to the minus 6, and that's in volts. Okay, so once again, we had to solve that circuit 3 times. Once for t less than 0, so we could get our initial voltage. Once for t going to infinity, so we could get our final voltage. And once for t greater than 0, but the source is killed, so that we could get our tau. Okay, similar circuit here. We'll work through. Once again, we're trying to find the capacitor voltage. It's labeled in this way. So what do we have to do? We have to solve for the circuit at t less than 0 when t is equal to 0 minus, so it's been sitting for a very long time. We need to solve for t greater than 0 with the source is killed to find tau. And then we need t going to infinity to find V final. So let's do that in order. So sketching the circuit for t less than 0, plus minus 120 volts, 3K, 9K, and you will notice that when the switch is in position A, everything else is unhooked, and the capacitor was actually in parallel with the 9K. So at 0 minus, that's going to look like an open because it's been sitting for a very long time. It looks like DC. So the initial condition on that capacitor voltage does not change instantaneously. So at 0, we'll have a voltage divider ratio. And you should get 90 volts. Okay, now let's look at the circuit after the switch moves to position B. So we'll have a 20 nanofarad capacitor. The 10 kilo ohm is here. The 40 kilo ohm is here. And there was a current source here. Now remember, for finding the time constant, we have to kill the current source. So to kill it, we basically pull it out, replace it with an open circuit. The tau will be the resistance seen by the capacitor with the source killed. So it'll actually be a series combination of 10K and 40K, so our equivalent will be 50K, so tau is RC, which is 50, 20, 10 to the third, 10 to the minus 9, so it is 1,000, looks to me like it's going to be 1 times 10 to the minus third, if I'm correct and didn't make a math error. Alrighty, so let's see, yeah, that's 1,000 times 10 to the third, that's 1 times 10 to the 6th times 10 to the minus 9th is 1 times 10 to the minus third. Okay, now let's find V final. So VC at infinity. Working off of this circuit, see if I can just erase. Nope. So let's come back. I'll just redraw it. So we had our 20 nanofarad capacitor at infinity, so at t going to infinity. Our 20 nanofarad capacitor is going to look like an open. We have 40K here. We have 40K here. We have 1.5 milliamps. And note that all of the current will go through the 40K resistor, giving you a voltage of 1.5 milliamps times 40K, or 60 volts. Notice that the polarity is in this direction. Our original voltage polarity was in this direction, the opposite direction. So VC at infinity will be negative 60 volts. So plugging in, V of t is my final value, which is minus 60, plus my final value minus my initial value, e to the minus t over 1 times 10 to the minus 3. And we can do a little simplifying. Minus 60 minus 150 e to the minus t over 1 times 10 to the minus 3. Okay. So that's an example with a capacitor. So to summarize what we've looked at, basically we've looked at 3 examples over the last 2 videos. 1 with an RL and 2 with an RC. And we applied this formula shown here at the top of the page, and we basically said that overall the general approach is you have to take 3 steps to solve the circuit. First, you want to find the initial condition. So you want to look at what the situation was on the inductor current or the capacitor voltage right before any switches moved. So we call that 0 minus. At that point, inductors will be shorts, capacitors will be opens. So really the circuit typically gets pretty easy to solve, and you're just looking for what is the current where the inductor would have been, what is the voltage where the capacitor would have been, and that gives you this x sub 0. Then you look at what happens after the switch moves, and you find the Thevenin resistance as seen by the inductor or capacitor, depending on which one it is. So you kill all the sources in the t greater than 0 circuit. You look at what resistance is seen by the storage element, and then you take, for inductance it's L over R, for capacitance it's RC. Then you let time go to infinity. So once again, you're still working with the t greater than 0 source, or the t greater than 0 circuit. You put the source back in, and as t goes to infinity, once again the circuit approaches DC. So the inductors will go to shorts, the capacitors will go to opens, and you'll be able to find the final value for the capacitor or inductor current using really DC circuit analysis techniques. So as long as you solve your circuit essentially 3 times for 3 different situations to get your initial value